Thank you for the introduction. Can everyone hear me at the back? Yeah? Okay, so I'm going to start giving the first talk. The first talk is about uncovering access, reuse, and sharing characteristics of I/O-intensive files on large-scale HPC production systems. So you might wonder why we care about I/O on HPC systems. Well, the truth is that I/O is becoming a severe bottleneck in large-scale HPC systems. In improving the performance of the HPC systems, we tend to focus more on the compute side of things and less on the I/O side of things. But as HPC applications are becoming larger and larger, they also need to perform more and more I/O, be it checkpoint I/O or data analytics I/O. And this I/O needs to be analyzed from the perspective of the I/O-intensive files. So for this reason, we perform an in-depth characterization and analysis of access, reuse, and sharing characteristics of I/O-intensive files on a top 500 supercomputer. And the supercomputer that we use is the Cori supercomputer, which is housed at NERSC. So we look at the data for a period of approximately 4 months, spanning 84 million logs, 52 million files, 9,000 applications, and over 600 users. And the total data of the total amount of I/O transfer is about 13 petabytes. So some examples of the kind of analysis that we do is whether HPC files are read-heavy or write-heavy or both, if sharing a file across multiple applications exists, or if I/O variability exists within a single run and across multiple runs. So in terms of our study platform, we look at the shared parallel storage system, which is attached to the Cori and Edison supercomputers. In terms of the size, Edison is much smaller than Cori, and it was also recently decommissioned. That's why we focus on the jobs which were submitted on the Cori supercomputer. And these jobs perform I/O to the Scratch subsystem, which is the shared parallel storage system. So in terms of the architecture of the system, in the left figure, we show the entire flow of the data. So in the left of this figure, we have the compute nodes, and these nodes house the Lustre object storage clients. And these clients submit the I/O requests via the I/O nodes, or the ION nodes, and through the storage fabric, which is based on InfiniBand, these requests finally make it to the Lustre object storage servers, or the OSSs in the backend. And these OSSs make the I/O requests to the OSTs, which actually store the data. So in this particular Lustre-based file system, we have 248 OSSs and corresponding 248 OSTs. So there is one target per server. So you can imagine that at max capacity, a file can perform parallel I/O to all of these OSSs, improving their performance considerably. But of course, this is only theoretical. In reality, we have quite different results, as we will see later. So for I/O monitoring, we use the Darshan I/O monitoring tool. And this tool provides monitoring at 3 different levels. So one is at the application level. So at the application level, we get data from the Slurm job logs, such as the application ID, executable ID, user ID, project ID, and start times and end times of the application. Then we also get I/O data at the I/O request level. So we trace exactly how many I/O requests are taking place, what is the total amount of data that was read and written, what is the total amount of data per rank, how much time it took for each rank to perform its I/O, the type of I/O interface used, and many other statistics that Darshan actually monitors. And then the last layer is the Lustre file system layer. And at this layer, it monitors the type of OSTs that were used, the number of OSTs that were used, and the stripe width of the file. So the stripe width here refers to the number of OSTs to which a file was actually written. So in an HPC parallel file system, you can actually break a file down into multiple chunks, and they can be striped across these multiple targets. So before we present our analysis, I'd like to establish the scope of the study. So we make sure that the findings may be true for other systems, but we don't actually make this claim. So inherently, our findings are influenced by the policies at NERSC. This includes whether the default stripe is 1, which is for all the users at NERSC, or whether the file system is Lustre-based, as opposed to any other file systems, and also is influenced by the workloads which actually run at NERSC. Another thing we note is that our study is bounded by the information which is available in the Darshan I/O monitoring tool. So it does not monitor things such as what is the actual size of the files. It monitors the amount of data that was transferred for the files, but not at individual file level, because the monitoring is at the application level. And lastly, we note that while the Cori storage system does have an SSD-based data warp burst buffer system, This burst buffer has very limited usage. So currently it receives only 5 to 15% of all of the I/O traffic. So we don't actually analyze this burst buffer data because it doesn't affect the validity of our findings as of now. But if burst buffers were to become more prominent in the future, then the findings may have to be revisited. So before we start our analysis, I'd like to define some terms and definitions. And while doing this, we'll also come across some other insights. So the first thing is to identify I/O-intensive files. So as I mentioned earlier, we saw that there were over 53 million files. But as this heat map shows, on the x-axis, we have the total amount of data transferred for each of the files during the 4 months. And on the y-axis, we have the number of runs which were actually accessing these files. So a run here is just one instance of an application executable. So we see that most of the files were actually only accessed once, and they perform less than 1 gigabyte of data. And these files are clearly not the HPC I/O-intensive workloads that we're looking for. They may be user logs or error logs or executables or any other metadata type files. But we want to focus on large-scale applications and their I/O. So we look at files which produced at least 100 gigabytes of data during the 4 months, and also were accessed at least twice, which shows their significance. So when we do this filtering, we're still left with 8 petabytes of data transfer and over 400,000 jobs. So once we've identified the I/O-intensive files, the next step is to actually classify them based on their I/O type. So in this heat map over here, the x-axis shows the amount of data that was read during the entire 4 months, and the y-axis shows the amount of data that was written. And note that the axis is in log scale. So here we have 3 distinctive chunks. In the top right corner, we have the files which were both read and written, and these constitute 71% of all files. So we refer to these as read-write files. In the top left corner, we have the files which were only written to during the 4 months, and they were never read. And these files we refer to as write-heavy files, and these are only 7% of the files as one would expect, because one wouldn't expect that a lot of I/O is being performed, but it's never utilized. And lastly, in the bottom right corner, we have the read-heavy files. And these files only perform read data, and they were never written to. And these files are actually 22% of all the files. So almost a fourth of all the files on this HPC system were never actually written to. They were only read from during the 4 months. Next thing we look at is how do we actually classify these runs which are accessing these files. So we would expect that HPC applications are assumed to perform both read and write I/O during the same execution instance or a run, just in different phases of I/O. So we would expect that it performs some sort of a write, and then it reads the data, and then writes the data or reads the data at different I/O phases during its execution. But when we actually analyzed the data, we saw something quite opposite. So here the x-axis shows the difference between the amount of I/O data that was read and the amount of I/O data that was written, divided by the total amount of the I/O data that was read and written during the entire 4 months. So if this value is close to 0, that means that the amount of the I/O data that was read and written per run is exactly the same. And if this value is close to 1, that means during a run, either only the reads were performed or only the writes were performed. As you can see here, the histogram of this particular distribution is completely empty because we only have 1 bar on the right over here, which means that over 80% of the files, over 80% of the runs either only performed reads and writes. And this indicates a significant departure from traditional monolithic HPC workloads which perform all of the I/O in the same workload. Instead, we're moving towards scientific workflows which have multiple applications which are interdependent on each other, and they perform I/O which is interdependent on each other. So some applications write the I/O and some applications read the I/O. And we can actually leverage this insight to avoid I/O contention among different workflows by organizing these different applications in a way that they don't contend with each other. So for our further analysis, we actually split it into 3 parts. The first thing that we look at is file reuse patterns. Then we look at the data transfer characteristics. And then lastly, we look at the I/O variability characteristics. So in terms of file reuse patterns, the first question to ask is, how often are these files getting reused? And are they getting used consecutively in terms of reads and writes? So in this simple illustration, we show what we mean by this. So there's this one file, and it is getting accessed by a write run, as indicated by W, and then 4 read runs, as indicated by R, and then a write, and then a read, and then 3 write runs. So here we would define interarrival times of write runs as the difference between difference in time of the start times of 2 write runs, as shown in the bottom left over here. And for read runs, it's the same, but for reads. And the number of consecutive read runs is the number of consecutive read runs without being interrupted by any write runs in between. So in this case, we have 4 consecutive read runs and then 1 consecutive read run. And for writes, we have 1 consecutive write and 1 consecutive write and then 3 consecutive writes, and so on and so forth. So now we'll look at the distribution of the inter-arrival times. So in these 2 plots, we have the CDF of the inter-arrival times of the read runs on the left, and then the inter-arrival times of the write runs on the right. And here we see that while some of the files have very small inter-arrival times in terms of read runs and write runs, most of the files have an inter-arrival time of over 55 hours. And this is consistent for both read runs and write runs. So while the files are getting reaccessed, they're not getting reaccessed frequently enough. We have enough time in between 2 runs to be able to perform some sort of an optimization. So one can imagine that once a file is accessed, you can actually compress the data and put it in backend storage in order to reduce its capacity. And when we expect the next inter-arrival to occur and the file to be accessed next, we can uncompress the file and move it up to, and prefetch it up to the caching layer, which is the burst buffer layer. And we have this kind of capability because we have a multi-tier storage system. And then again, once the file is done, then we can move it back to the storage layer. So in this case, not only can we save on capacity, but we can also actually make use of this multi-tier storage system to reduce the contention at the backend storage system. So in terms of the number of consecutive runs, here we have, again, the CDFs of the number of consecutive read runs and the number of consecutive write runs. And we see that most files actually have alternating read and write runs. So we see that over 50% of the files actually have less than 2 consecutive read or write runs. But with reads, we see that the average number of consecutive runs is actually 14. And this is because of the fact that there are a lot of read-heavy files. And these files only get accessed using read runs, as we noted before. So we can partition I/O servers to actually separately serve read-heavy files and read-write files. Read-heavy files do not need to get interference from the write runs, and certainly read-write files, which are getting consecutively and alternatively accessed by read and write runs, can afford to have a separate server subsystems where they can perform I/O without having interference from the read-heavy files. So now that we have established the inter-arrival times and the type of runs, next we'll look at how the files are actually shared across different applications. So traditionally, with monolithic scientific workloads, we would expect that the same file only gets accessed by one application. But this is no longer the case, as we saw earlier, because we're moving towards scientific workflows. So we can have cases where 2 applications access the same file. And in fact, that is what we see in practice. So this CDF shows the CDF of the number of applications accessing a single file. And as we see here, over 67% of the files get accessed by at least 2 applications. And these are not just read-heavy files. So with read-heavy files, because they're never getting written to, we might expect that a user writes to them and then uses multiple applications to actually read from them. But we see that 86% of the files that get accessed by multiple applications are actually read-write files, which means that there is a clear producer and consumer relationship where some applications are serving as the producer and the others are serving as the consumer. But it's not as simple as just saying that a producer is writing the I/O, so we can expect that the consumer will be reading it in the next few hours. Because as we see here, when we look at the inter-arrival times of these applications, the average inter-arrival time is 31 hours. So the producer and consumer are launched significantly apart in time. So we cannot perform caching right away. We have to be careful when we're actually prefetching the producer data towards the upper storage layers, because we want to be able to predict accurately when the consumer will exactly access these files. And this requires some extra work. So next we look at the data transfer characteristics for each of the I/O runs and for each of the OSTs. So in terms of I/O runs, because we know that the total amount of read data during this 4 months was higher than the total amount of write data, and we also know that there were many more read runs than write runs, one could expect that the amount of read data per run would be higher than the amount of write data per run. But in reality, what we see is the opposite of this. So here we have the CDF of the amount of read I/O data per run and the amount of I/O data per write run. And with these CDFs, we actually note that most of the runs have little amount of read and write data. As we can see, over 80% of the runs have less than 12 gigabytes of read and write data per run. But on average, write data is 25 gigabytes per run, while read is only 17 gigabytes. And the reason for this is that there are few runs which are performing a lot of writes simultaneously in the same run, which means whenever applications are performing their writes, they're doing a lot of writes, but whenever they're reading it back, it's in chunks and pieces, so they're not reading all the data back in the same run. And this can be expected if we have producer-consumer relationship, where the producer produces all the data simultaneously, while consumers are consuming them in bits and pieces as is required. But this can be actually exploited to manage I/O contention better at the system level by limiting the number of concurrently running write runs, because we know that write runs are the ones which are doing a lot of write data at once. So next, when we look at the OST I/O transfer rate per run, we know that on Lustre, OSTs are capacity balanced, which means that each OST approximately has the same amount of I/O data that is stored. So we would expect that they would also have similar amount of data transfer for all 248 OSTs. But when we look at the data transfer rate for these individual OSTs, we see results that are quite different. So here on the x-axis, we have individual OSTs, and they're sorted by the total amount of I/O data transferred for each of the OST. And we see that the minimum OST, which has the minimum I/O data transfer rate, actually only transfers less than 20% the amount of data as the OST which transfers the most amount of data, which means there's a lot of imbalance among these OSTs in terms of the amount of I/O data that they transfer. And this is in spite of the fact that other statistics, such as the number of applications which are accessing these OSTs, number of files which are stored on these OSTs, and the number of users that are accessing these OSTs are more consistent for all of the OSTs. But the amount of I/O data transferred still varies considerably. And this highlights the need for dynamic file migration, especially if we know that some files are likely to be accessed over and over again, such as read-heavy files. Then there is a need to migrate them on more stable OSTs so that we have balance across these OSTs. And there's also need for replication of read-only data. Because if we're only reading the data, then we don't actually care which OSTs we're reading from. So if certain OSTs are more contended, then if we have replicated data, then we can actually use other set of OSTs to read that data at a faster pace. And this brings us to I/O variability. So I/O variability can actually be caused by this contention at the OST level, as well as the contention from other applications. So that's why we look at both types of I/O variability. One is the intra-run I/O variability, and the other is the inter-run. So I'll explain what I mean by that. So for intra-run I/O variability, we know that HPC applications have hundreds of thousands of ranks or processes which are performing I/O at the same time. And if it's performing I/O in a good way, then all of these processes should be performing I/O to a diverse set of OSTs as opposed to the same one, in order to make use of the parallel features that are available. So here in this example, we have 4 OSTs, and we see that application A is performing I/O on all 4 of its OSTs through either different processes or the same file striped across different OSTs. But we see that on the last OST, there is also an application called application B. And this means that on the last OST, application A would actually face higher contention. So even if the processes on the other 3 OSTs finish faster, this doesn't necessarily contribute towards application A finishing its I/O phase any faster, because it still has to wait for all of the slow ranks to finish, thus wasting precious compute cycles. Sorry, my screen disappeared. Yeah. So that would be our hypothesis, that there should be intra-run I/O variability based on different contention at different OSTs. And that is exactly what we see in our results. So in these results, let's look at the first plot on the left here. So we have 3 different types of I/O interfaces which are most commonly used: POSIX, MPI, and standard I/O. And standard I/O is obviously going to be used the least because we are talking about HPC applications. And the y-axis plots the amount of I/O data transferred for each of these interfaces per run. And we see that POSIX and MPI I/O transfer over 200 gigabytes of data per run. And the second plot in the middle shows its standard deviation of the amount of I/O data transfer per rank for MPI I/O, POSIX I/O, and standard I/O. And again, we see that each rank has very low standard deviation, even for POSIX IO. So for POSIX IO, the standard deviation among the rank IO size is 1.5 gigabytes. But this is negligible when we compare it to the overall IO size of 250 gigabytes in the first figure. So we see that all of the ranks are performing approximately equal amount of IO. But when we look at the last figure, which shows the standard deviation of rank IO time, we see that this time can actually be up to 50 seconds for POSIX IO. So even though all of the ranks are performing the same amount of IO, we see that they're actually taking different amount of times to finish their IO. And this difference can be up to 50 seconds, which is quite slow, especially considering that the system has a maximum bandwidth of 744 gigabytes per second. So we see that there is high variability in IO time of ranks per process with similar IO size belonging to the same application. Next, we'll look at the inter-run IO variability. So inter-run IO variability can occur when the same application running at different times is contended with different types of applications. So here we see application A running with application B at time T1, but then at time 2 it's running with application C. And this can cause different contention levels, even if application A is performing the exact same IO. Because the parallel storage system is shared among the applications, we can expect variability because of this. And we do see these results in our analysis. So the first plot over here shows the coefficient of variation of IO size across the runs. So coefficient of variation is essentially standard deviation as a percentage of the mean. So when we look at the IO size across the runs, we see that the coefficient of variation is actually close to 0 for over 70% of the files, which means that the amount of IO that they are transferring from one run to another is not actually changing significantly. In fact, the mean COV is only approximately 12%. But when we look at the COV of IO time from one run to another, we see that on average it's almost 40%. This means that even though the IO size is not changing as much, the IO time is varying considerably. And this is in part due to the contention at different OSTs as well as contention from different applications. And this contributes significantly towards the variability in the IO performance and hence the entire performance of the HPC application. In our paper, we also provide more analysis on temporal IO characteristics of how they vary based on time and the impact of that on the overall IO runtimes of the application, and you can refer to the paper for that. So in conclusion, there's an open opportunity to leverage the favorable characteristics of HPC IO, and many of these characteristics are actually new because of the changes in the HPC workloads. These include classifiable files, single IO type runs, long interarrival times, which are quite consistent, as well as these can be used to better manage HPC IO. There's also lack of coordinated IO management at the OST level, which exacerbates the IO variability and contention challenges. And we will tackle one of these challenges in the next talk that I'm presenting. And lastly, there's inter-run and intra-run IO variability, which not only causes runtime variability, but also waste IO bandwidth and compute cycles. And again, we will be challenging the inter-run IO variability in the next talk. And that concludes my presentation. Thank you.
Questions? Everybody's getting tired. All right, I'll go in. So first of all, thank you very much for doing this. It's always nice to see new workload analyses come out to give us a better idea of what high-performance workloads actually look like right now.
Right.
And kind of to that point, so you mentioned that this may not apply to other systems outside Cori at NERSC, right? Mm-hmm. But just kind of digging into that a little bit, what do you think could translate to other HPC systems, particularly systems that have, so I remember correctly, Cori has very, very high utilization. And right. I'd be interested in how you think some of these insights could translate to other HPC systems that are maybe commercial HPC systems.
I think most of these insights would translate quite directly to other systems as well, especially if they're Lustre-based. So for example, the OST contention challenge that I mentioned, they're quite common across a variety of systems because Lustre does not tend to load balance the OSTs, it tends to capacity balance them. And because a lot of HPC storage systems end up using Lustre, so we have that problem across all of these systems. As well as the scientific workloads which are used at NERSC are also common with other HPC storage systems as well. such as LAMPS or any other scientific simulation workloads. And because they're also moving towards more scientific workload type nature, they would remain consistent for those systems as well.
So do you think scientific workloads are kind of key to this? How about non-scientific workloads?
I think it's both the things. So one is the type of workloads that are running, so it can be DNN workloads as well, or any other data analytics type of workloads which do a lot of I/O. But it's also the architecture of the system itself, right? So it can be, whether it's multi-tier, so the Cori system has burst buffer layers, but some systems might not, so that might affect the results a little bit, even though the burst buffers at Cori are not used as much. But it can also be other sisters, so like the file system, as I mentioned. Yeah.
Thank you.
Yeah.
Does anybody else have a question? They just want to hear his next talk. He's like, set it up so nicely. All right. Well, let's thank the speaker and let him speak again.